Friends, welcome to the class. Today we'll discuss about some questions on real numbers. We have already discussed real numbers with some examples. Today we'll discuss some more questions of real numbers. The first question states, use Euclid's division algorithm to find HCF of 867 and 255. The given numbers are 867 and 255. Here 867 is greater than 255. Let A equals to 867 and B equals to 255. Now, according to Euclid's division formula, for any two numbers A and B, we can have another two numbers such that A equals to B cube plus R, where 0 less than equals to R less than B. So, applying Euclid's division algorithm, we can write 867 to be equals to 255 into 3 plus 102. Here, A equals to B cube plus R. Here, A is the dividend, B is the divisor, Q is quotient, and R is the remainder. So when we applied Euclid division algorithm, here we got remainder to be 102. We have to repeat the same process unless and until we get remainder to be equals to 0. The moment we get 0, then we can find the HCF. Here the remainder is 102 and 255 is greater than 102. So again, applying Euclid's division algorithm, we have 255 equals to 102 into 2 plus 51. That means here also we got the remainder to be equals to 51, not 0. Again, applying Euclid's division formula, we have 102 equals to 51 into 2 plus 0. So here the remainder is 0 and the divisor is 51. Hence, HCF of 867 and 255 is 51 is the answer. So that the cube of any positive number is either of the form 9m or 9m plus 1 or 9m plus 8. Let us consider an arbitrary positive number x. By taking x as dividend and 9 as divisor, we can have x equals to 9q plus r, where 0 less than equals to r less than 9. So the value of r can be 0 or 1 or 2 or 3, and it continues up to 8, but r cannot be equals to 9. So x is any one of them. That means x may be of 9q or 9q plus 1 or 9q plus 2 or 9q plus 3 and so on up to 9q plus 8, because we have taken 9x to be equals to 9q plus r, and the value of r is in between 0 to 8. So x may take any of this form. Let us consider x equals to 9q. So x cube equals to 9q whole cube, which is nothing but 729 q cube, or it is 9 into 81 q cube, or we can write it as x cube equals to 9m, where m equals to 81 q cube. Now let us consider x equal to 9q plus 1. Now x cube equals to 9q plus 1 whole cube, which is nothing but 729 q cube plus 243 q square plus 27 q plus 1. Or if we take 9 common, we can write it as 9 whole into 81 q cube plus 27 q square plus 3q bracket ends plus 1. Or it can be written as x cube equals to 9m plus 1, where m is equals to 81 q cube plus 27 q square plus 3q. Now let us consider if x equals to 9q plus 2. Now x cube equals to 9q plus 2 whole cube, which is nothing but this simplifies x cube equals to 729 q cube plus 486 q square plus 54 q plus 8. Or if we take 9 common in the first three cases, for the first three terms, we get 9 whole into 81 q cube plus 54 q square plus 6q bracket ends plus 8. Or we can write it as x cube equals to 9m plus 8, where m equals to 81 q cube plus 51 q square plus 6q. Let us consider x equals to 9q plus 3. So when x x cube equals to 9 cube plus 3 whole cube, or we can write it as on expansion we get x cube equals to 729 q cube plus 729 q square plus 243 q plus 27. Taking 9 common, we get 9 whole into 81 q cube plus 81 q square plus 27 q plus 3. That means it can be written as x cube equals to 9m, where m equals to 81 q cube plus 81 q square plus 27 q plus 3. Now let us consider x equals to 9q plus 4, and let's see the result. X cube equals to 9q plus 4 whole cube, or it is equals to 729 q cube plus 972 q square plus 432 q plus 64. For taking 9 common in the first three terms, we get 9 whole into 81 q cube plus 108 q square plus 48 q plus 7 whole into bracket ends plus 1, or we can write x cube to be equals to 9m plus 1, where m equals to 81 q cube plus 108 q square plus 48 q plus 7. So friends, here we have taken x is any of the form 9q or 9q plus 1 or 9q plus 2, or it may be 9q plus 8. But in the first 5 cases, when we took x equals to 9q or 9q plus 1 or 9q plus 2 or 9q plus 3 or 9q plus 4, we got x cube, that is cube of the positive number, either of the form 9m or 9m plus 1 or 9m plus 8. Apart from these three forms, we didn't get any other form. Similarly, if we go for further expansion, we'll get the same results, whether for 9q plus 5 or 9q plus 6 or 9q plus 7 or 9q plus 8, we will get x cube either of the form 9m or 9m plus 1 or 9m plus 8. So it is clear that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Hence proved. An army contingent of 616 members is to march behind an army band of 32 members in a parade. Two groups are to march in the same number of columns. What is the maximum number of columns in which they can march for? So it is clear that HCF of 616 and 32 gives the maximum number of columns in which the groups can march. Let's go for finding the HCF. Using Euclid's formula, it is clear that 616 is greater than 32. So applying Euclid's division lemma, we get 626 equals to 32 into 19 plus 8, because it is of the form dividend equals to divisor into quotient plus remainder. When we get remainder to be equals to 0, the divisor will be the desired HCF of the given two numbers, that means 616 and 32. So here the remainder is 8. So again we have to follow the division again. Here the remainder is 8 and it is not equals to 0. So applying Euclid's division lemma again, 32 and 8, we get 32 to be equals to 8 into 4 plus 0. So here the remainder is 0 and divisor is 8. So the HCF of 616 and 32 is 8. Hence, maximum number of column is 8 in which they can march. Is the answer. Using Euclid's division lemma, so that the square of any positive number is either of the form 3m or 3m plus 1 for some integer m. Let us consider an arbitrary positive number y. Then by taking y as dividend and 3 as divisor, we can write y equals to 3q plus r, where 0 less than equals to r and less than 3. That means the value of r can be 0 or 1 or 2. If r equals to 0, we get y to be equals to 3q. So y square is 3q whole square, which is nothing but 9q square, or we can write it as 3 into 3q square. So we can write y square equals to 3m, where m equals to 3q square. Let this is first equation. If r equals to 1, we get y equals to 3q plus 1. So y square is 3q plus 1 whole square. On expansion, we get y square to be equals to 9q square plus 6q plus 1, or taking 3 common in the first two terms. 3 whole into 3q square plus 2q plus 1. Or we can write it as y equal to 3m plus 1, where m is 3q square plus 2q. Then this is second equation. Considering r equals to 2, we get y equals to 3q plus 2. So y square equal to 3q plus 2 whole square, or it is nothing but 9q square plus 12q plus 4. Or taking 3 common, it is 3 whole into 3q square plus 4q plus 1, bracket ends plus 1. Because here it is 4, so we have divided it as 3 plus 1. 3 into 1 is 3 plus 1. So y square is nothing but 3m plus 1, where m equals to 3q square plus 4q plus 1. This is the third equation. So from equation 1, 2 and 3, we got y square either of the form 3m or 3m plus 1. Thus, the square of any positive integer is either of the form 3m or 3m plus 1 for any integer m. Hence proved. Prove that root 5 is an irrational number. Let us assume that root 5 is an irrational number. So we can write root 5 in the form of ratio, that means in the form of p by q for some integer p and q where q not equals to 0. So if root 5 equals to p by q, we can write q into root 5 equals to p. So root 5 is a factor of p, but it contradicts the statement that p and q are the coprime. Now friends, what is coprime? Coprime means two numbers p and q are said to be coprime if there exists no common factor other than 1. But here we got root 5 is a factor of p. That means it contradicts the statement that p and q are coprime. So our assumption is wrong. Hence, root 5 is an irrational number. It's proved. There is a circular path around a sports field. Ajay takes 80 minutes to drive around the field, while Saina takes 20 minutes to drive the same field. If they start at the same time, at the same point, and go in the same direction, after how many minutes they will meet again at the starting point? So given that Ajay takes 18 minutes to drive the circular path, while Saina takes 20 minutes to drive the same field. Now the desired result, the LCM of 18 and 20 will give the exact number of minutes they will meet at the starting point. Now 18, if we go by the prime factorization, 18 equals to 2 into 3 into 3, and 20 equals to 2 into 2 into 5. Now LCM of 18 and 20 is nothing but 2 into 2 into 3 into 3 into 5, which is nothing but 180 minutes. So Ajay and Saina will meet the starting point after 180 minutes. Is the answer. If n is an odd integer, so that n square minus 1 is divisible by 8, we know that any positive integer is of the form 2q or 2q plus 1. Since n is an odd integer, it is of the form 2q plus 1. Now n square minus 1 equals to 2q plus 1 whole square minus 1, or on expansion we get it is 4q square plus 4q plus 1 minus 1. So plus 1 and minus 1 gets cancelled. Plus 1 and minus 1 gets cancelled, or we get n square minus 1 equals to 4q square plus 4q. Taking 4q common, is 4q whole into q plus 1. Now for any integer q into q plus 1 is either 0 or even. So we can write q into q plus 1 equals to 2m, where m is a whole number. Now we can put the value q into q plus 1 in this case, n square minus 1. Now n square minus 1 is 4 into q plus 1, but already q into q plus 1 equals to 2m. So we can write it as 4 into 2 into m, which is nothing but 8m. So n square minus 1 equals to 8m means it is divisible by 8. Hence, for any odd integer, n square minus 1 is divisible by 8. Hence proved. Prove that if a, b, c and d are positive rational numbers such that a plus root b equals to c plus root d, then either a equals to c and b equals to d, or b and d are squares of rational numbers. It is given that a plus root b equals to c plus root d for some positive integers, for some positive rational numbers a, b, c and d. Since it is a plus root b equals to c plus root d, equating on both axes we get a equals to c and root b equals to root d. If a equals to c, then root b equals to root d, or in squaring the right hand side we get b equals to d. Now if a is not equals to c, then there exists a positive rational number such that a equal to c plus x. So we can write c plus x plus root b equals to c plus d root d. In the place of a, in the place of a we have used c plus x. So c plus x plus root b equal to c plus root d. Or we can write x plus, cancelling c on both sides, we get x plus root b equals to root d. Now squaring on both the sides, we get x square plus b plus 2x root b equals to d. Or we can write root b equals to d minus b minus x square whole divided by 2x, which is a rational number. Here d minus b minus x square by 2x is a rational number. That means root b is a rational number, or b is a square of a rational number. But we have root d equals to x plus root b. Since b is a rational number, or we can say root b is a rational number, x plus root b will also be a rational number. So we can write root d is a rational number, or square of root d. That means d is the square of rational number. Hence either a equals to c and b equals to d, or b and d are square of rational numbers. Hence proved. Friends, here is a few questions. Practice more and more such questions, and in case you come across any difficult question, share your question with me. It will be a pleasure for me if I can help you out in solving your doubts, in solving your question. So this much for today's class. Thank you.